test. Test. Okay, working. 2 seconds plus. Okay, good afternoon, everyone. Only 11 students. I think assignment 6 have about 8 students finish. 8 or 10, I haven't checked. Yeah, just now I saw it's about 8 students. Complete. Yeah. So it should be okay with the test cases. I think a few issues, I received hundreds of emails in the past few days about those things, a few things. First is the, delete slot. Okay, so one common issue is you think about it. If today you have a hash table, you're trying to delete one of the slot, then next time you're trying to reinsert. Okay, first deleted slot, you should not go and read it. Secondly, when you reach that deleted slot, can you insert it directly? Seems you cannot. Because how do you know behind no more the same number? How do you prevent the duplicate issue if you insert it immediately? Okay, that is one thing, yeah, you maybe haven't considered, because delete and empty slot although they are delete slot, they're supposed to be considered kind of an empty slot, but it may not be exactly same as the truly empty slot. Yeah, they are not exactly same as that. Yeah, you need to consider that. Yeah, delete slot behind still got some number. Yeah, you need to check. Okay, so that is a lot of people didn't consider the issue, the duplicate issue. Yeah, when you encounter a deleted slot, you not really can insert it directly for hashing. Second problem, that one is when the table is full. Okay, you check till the end. Yeah, just unfortunately the last item you check is a duplicate item. So I think common sense, I don't know, for me I feel is like I definitely have to check through that last lot. Then I find it's the duplicate, I will just return it is a duplicate, cannot insert. Then if it's not duplicate, then I find that the table is full already. Yeah, it's already the last item. Okay, so the table is full. So I return table is full. So priority should be duplicate first. You need to check until the last one, then you can confirm it is a full table. Yeah. Okay. Can we assume that all? Yes. I think I'm not too sure which assignment you refer. For if you're talking about assignment 5, all the algebra expression is valid. Yeah, I didn't key in the invalid expression. Otherwise, the thing can be a lot of combination already. It's very complicated already. I can type in anything I like. Then of course you it's very hard for you to do. Yeah. So that will be okay. So today I will cover the graph problem, and then hopefully today can finish the breadth first search and depth first search. Then if not, maybe next Monday we'll cover a little bit depth first search. Okay, if cannot complete today, then after that next Monday will be cover the Edqueen problem, and and the matching problem, all those things. Yeah, that one I'm still thinking. I'm still preparing the assignment. So assignment, the last assignment, I can confirm is 4 question. Yeah, I still left the last question. I still design the last question. Hopefully tonight I can finish it. Then I will release tonight or tomorrow. Yeah, if tonight cannot finish, tomorrow I'm also not free. So probably Friday. Yeah, I hope today can finish. Then can release on Friday. Of tonight, or if not, and probably only Friday I can do it. Yeah, but that one will go all the way till week 13. The deadline will be week 13, so you have a lot of time to think that 4 question how to do it. For assignment double hashing, we are not allowed to brute force search, and that miss the purpose, right? Yeah, miss the purpose, right? If you do the hash table, then you still search the whole table, use the brute force to search the whole table. Yeah, then why you make a hash table? Yeah, so definitely the search, you still need to follow the double hashing approach to search whether there's a duplicate or not. Yeah. Okay. Overall, seems like this module, the lecture attendance rate still very low. Normally it's 20, 30, then later maybe go to 70. Yeah, 600. Interesting is like a lot student haven't start your assignment. Another 2 thing I have to remind you that the submission is okay. Not, I think you should know that they will take the first best attempt as your final submission. So, and don't worry, I will not add any last minute new case. So yeah, I know that some question I didn't fully test. Sometimes you have done some funny things that you still can coincidentally, maybe you make, I saw some people make 2 mistakes. Yeah, first starting count wrongly, then later also count wrongly, then in the end overall still correct. Yeah, this a bit hard for me to find any test case to detect. Yeah, because you make one time you plus one, another time you minus one, and now overall still correct. Yeah, so that one a bit difficult. Yeah, so if it's correct, yeah, never mind, I just let you get the marks. Yeah, so it's still okay. Yeah, so, and some test case, I didn't realize that you will do that kind of mistake, so I didn't add those scenario. So, well, I will not do those tests. Yeah, if that's the case, this time round, maybe next time I will consider add more test case. uh Another thing is, yeah, I have to remind you, I probably will do some plagiarism check. Yeah, I see a lot of people still haven't start the assignment. Yeah, I can expect what you are going to do. Have to remind you. But well, I remind this 29 viewer, maybe no use. Those people also will not watch my video. Never mind. Let's see how. Okay, so yeah, I think Monday I already briefly tell you that what is the graph about. Graph have a lot of application, from the traffic, from the chemistry, to the computer network, to the electrical circuit, and a lot in our daily life. Even those problems, all these problems still can very obviously see there's a graph. Sometimes I think, yeah, you may see some problem, it doesn't look like a graph problem, but I can model it as a graph problem and solve it by any graph algorithm. Yeah, so that is the interesting of using the graph. Yeah, sometimes, yeah, you see the problem is doesn't, for example, yeah, later in the end of the last topic, I hope I should have a time to cover the last one, the matching problem. Yeah, you will find that actually, yeah, that one is the max 4 min card. Yeah, in our daily life, it can be used. For example, that maybe maybe I got something, I need some graph. In the PowerPoint, yeah, there are something here. I think you can see. There's a remove background. Yeah, you know this thing, actually at the back end, yeah, why they can instantly come out the background and foreground. Yeah, how they find out the background and foreground. I can add the something here. Yeah, keep the area, keep this area, keep this area. Yeah, keep all this area. Actually, this thing indirectly they are form a graph, and then trying to solve to find out where is the background, where is the foreground. Actually, it's also model the problem into a graph problem, and then solve it. Hey, why not working? Okay, never mind. But you find that yeah, this is one they're trying to model this background subtraction problem become a graph problem and then solve it. Yeah, so I don't want to keep discuss all changes. Backward. Can I recover back? Oh. Okay, never mind. Don't save it later. Okay, so yeah, it got a lot of. Yeah, I cannot. I have to. Hold on, I have to restart the thing. I miss out my on slide. Don't save. Open one more time. Okay. Yeah, so they are in our daily life a lot of problem. Actually, they are using graph. They model the problem. Today I have a problem like this one in the PowerPoint. They trying to want to find out where is the foreground, where is the background in the given picture. Then they trying to model this as a graph problem, and then trying to use some graph algorithm. This one we will that key algorithm I will introduce in the end to you. Yeah, that is how they look at the real world problem and then model it into graph and then solve it and solve the graph problem and then indirectly solve the real world problem. Yeah, that is the interesting part of the graph, and that's why you find out that the graph problem can have a lot of application in real world. So of course, first the challenge is the graph is like not like a tree. Tree you can quite easy to model it. That means there's a tree structure. Yeah, you know that binary tree you got two children for every nodes. So you can write your structure with two BT nodes pointer, left and right. Yeah, left and right. Then yeah, with the item, maybe integer, maybe charge, maybe whatever, some x. Yeah, left and right. Yeah, left nodes pointer and right nodes pointer to model this tree structure. But graph seems that not that easy. Yeah, and you can't build the whole graph in this manner directly. So, but sometimes maybe I don't really. Yeah, so people trying to model it, trying to look at the graph as the other way around. So they will introduce two type. Here I only introduce two representation. One is the adjacency matrix. The other one is adjacency list. But first, they're not limit to this particular two representation. But these two representation is what we commonly use. Therefore, why did the head size? Oh, okay. Before I carry on, okay, let me clarify for all the lab 6 or assignment. I think the hash size, the table size, hash table size. I decide the hash table size is just okay. That no special reason. I just want to decide a size to make sure that my alpha not too large or too small lah. Yeah. So probably not the common way, but well, I just need to create a site. So in fact, I don't even need to use the log factor. The log factor is just show you for fun only. Actually, it's nothing. You don't need to use it at all in the end. Yeah, I just for me to create a table, then with a maybe linked list, maybe whatever to store the data. Yeah, no special reason. So back to the lecture. So this graph, we can here I'm going to introduce two: adjacency matrix and adjacency list. So adjacency matrix basically is a 2D matrix. Okay, it's a 2D array or 2D matrix. Yeah, that means you have how many vertex? Let's say I got the graph have so many vertex. So maybe 1, 2, 3, 4, 5, ... 2. So I will create the corresponding matrix by V by V. So that means each row, each column represent the vertex 1, 2, 3, 4, 4, 5, ... to P. Okay. So then whenever the vertex there's a connection between 3 to 4, then I will assign 1. Yeah. If it's a UV is in E, is an edge. There's an edge to connect the U and V, vertex U and V. Then you will assign 1 to the corresponding element in the adjacency matrix, just like this. Otherwise, if there's no connection, then you will give 0. There's no edge between these two vertex, then you will give 0. You will assign 0. So so not surprising that if the graph is undirected, then the matrix should be symmetric. That means if it's undirected graph, 3 to 4 and 4 to 3, both should be equal to 1, or both should be equal to 0. So in the end, you should expect that this should be a symmetric. It should be symmetric. Okay, if a graph is directed, then adjacency matrix UV equal to 1. If and only if. If the graph is directed, I hope you still remember. Directed means that they only can from U to V, then cannot V to U. Then so only A U V is equal to 1, but it does not imply that VU is in E. Also not implied that adjacency matrix at VU equal to 1. Okay, so that is adjacency matrix. I think I have an example. For example, this one is just now what you see the graph. So 3, 7. In 3, 7, where is it? So this is the undirected graph. So the corresponding adjacency matrix will be look like this. So 3, 7 you can see here. It's here. So it will be assigned 1. So undirected graph, the corresponding 7, 3, also assigned to 1. Then 11, for example, 11, 1. 11, 1 is here. So 1, 11 also here. 1, 11 and 11, 1. These two should be equal to 1 because there's a link. There's an edge here between them. So you also can think undirected graph are bidirectional. That means you can go from here to here, also can here to here. So both were assigned to 1. The rest, which there's no edge, then they will assign 0. Like 1, 6, they are not connected. So 1 is here, 6 is here, they are not connected. So not surprising that should be 0. Yeah. So this is the good thing is like to use the adjacency matrix, I can you just provide me 2 vertex. Yeah, I can immediately tell you that whether they are connected or not connected. Because matrix I can instantly access. You just give me the index, the vertex number. I can go to that particular location to check. If it's 0, means that they are not connected. If it's 1, that means they are connected instantly. Yeah. So the access time for particular element is in constant time. You can immediately check they are connected or not connected. Okay. Another way is using the adjacency list. Adjacency list use an array. So basically it's an array, 1D array to represent the vertex. Yeah, so let's say I got so many vertex. That means this is vertex 1, represent vertex 2, vertex 3, and so on and so forth. To the last one is the number vertex V. Yeah, you got so many vertex, then you create an array with the same size. Yeah, then each vertex use a linked list. Yeah, so a bit look like your close addressing hash table. So they use a linked list behind to represent the connection of other. This means let's say 2 is connect to 3, they will indicate 3 here. Then maybe 2 also connect to 4, they will indicate here. Yeah, so this is adjacency list. So the access times to find out the adjacency matrix, adjacency list. Okay, sorry, this one should be L. Yeah, adjacency list. Yeah, later I should correct it. Okay, adjacency list is linear time because not surprising is a linked list. So you want to search which vertex is adjacent to the vertex 2. You need to take linear time to search along this linked list to find out 3 and 4 are connected, are adjacent to the vertex 2. So but the good thing is that the space complexity is V plus V. You compare to the matrix. Just now the matrix is V squared. What is the V and the E size? What is the V and the E size? Okay, this one is the V is the vertex, number of vertex. E is the number of edge. Yeah, which is this one. So this one is V. Yeah, of course C cannot write. C programming cannot write this symbol. So have to rename it. Yeah, this is the E. So yeah, this is just an example. That means I don't have to always have to write V size. You want to name whatever appropriate name you like is fine. Yeah, there's no any particular name, then it work. Yeah, I hope you know. Yeah. Of course I can add more element if I need it. Yeah, but definitely to construct a adjacency list, I need to know the number of vertex, number of edge. Then I need to have a list nodes double pointer because it's an array. That means it's or you can think this one is a list nodes array, a linked list array because you have a lot of linked lists. Yeah, then each linked list is a pointer, so that's why there's a double pointer. One of them is an array. Then the other one is the pointer. Okay. So you can see this one and this one. Okay, this one also same thing. Okay, here I noted. Yeah, this one should be E. Then this one is the 2D array. 2D array. So not surprising that the space complexity of this one, I think I should use a big theta because it's always number of V square. Okay, you won't change any circumsystem. Yeah, you definitely use so many vertex and so many edge. Yeah. So compare, I think the key is you compare these two. The key is you compare this one and this one. Yeah. Not surprising that this one is relatively lower. Because I think if you recall the Monday lecture, if you have a complete graph means that all of them are adjacent to each other completely. You can have this graph, this one connect to this one connect to this one. This one is a complete graph. That means in the complete graph, your E, in the worst case scenario, your E should be V times V minus 1 divided by 2, which is in V square. So that means this thing in the worst case scenario is in V square. Yeah, that means this one, the previous adjacency matrix is always V square. But the adjacency list is only in the worst case scenario, it is in V square. But yeah, it can be better. It can be better than that. If you have a very sparse graph, there's been very few edges. Actually, this one will be the number of edges. It can be much lesser than your number of vertex. Yeah, that's when this thing you can think that it can be in certain circumsystem is only in V. Yeah. When you have a very sparse graph, very few edges. Yeah. Okay. So in the linked list of a vertex A, the item in a list, in a nodes would be the address of in the linked list. Okay, if you're talking about adjacency list, yes, they trying to store the list nodes is the address. Is the address of the linked list. Is the address of the linked list. What is the value? So if it's an adjacency matrix, good question. Along here, we put 0. That means there's no this kind cell loop graph. Unless they have a 8 to 8, 1 to 1, that means it's like a cell loop. This node's adjacency to itself. Yeah. So, but I think here we do not have in graph theoretically it can be something like this. But here the problem we encounter, we do not have the graph something like that. Yeah. Because in later we talk about, we only introduce the breadth search and depth search in this module. So those problems not considered the cell loop issue. Yeah. So normally the graph don't have that kind of nodes. Okay. So next one, okay, adjacent. For example, this one, same thing. Just now what you see, exactly the same graph. Okay, so again, you have so many vertex. So if this one, you can see that this one I construct, I got 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So I got 12 vertex. my v is equal to 12. Then these are the edges. One is connect to, for example, this one is connect to 2, 3, 4, 11. Yeah, 2, 3, the linked list, there's a 2, 3, 4, 11, the corresponding linked list. Like 2 is adjacent to 1, 5, 6, 11. Yeah, 1, 5, 6, 11, and so on and so forth. So yeah, like 3, but you can see that if it's undirected graph, like this case is an undirected graph. So 3 in the 3 slot, the linked list contains 7. In the 7 slot, the linked list contains 3. Yeah, because 3 is adjacency to 7, 7 is adjacency to 3. Yeah, for undirected graph. So yeah, so not surprising, the question, yeah, the point here is this. So all the total number of nodes here is 2e. Yeah, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 edges. So you're not surprising that here got 24 nodes. You can go and count it. I don't have time to count for you. You can try to count. I give you some time to count. Yeah, 24 nodes. Expected because they are symmetric. So definitely you can find that there are always two nodes are corresponding, 3 to 7, 7 to 3. Yeah. So this is the, but it may not true in the directed graph. This is for undirected graph. Yeah. Then the number of nodes in the linked list, in all the linked lists, is 2e. Okay. So next. So okay, this is when I consider all the scenario is like when they are not weighted. So well, not too difficult. If I introduce the weight, so for adjacency list, you need to introduce another parameter to store the weight. Yeah, in the data field in the list nodes. For adjacency matrix, instead of assign 1 or 0, you're trying to assign the weight. Yeah. So sometimes, like I said, sometimes we may assign 0. Yeah, sometimes we also can assign those link are not connected. Those between two vertex there's no edges. Yeah, just now you see we assign 0. But sometimes in some circumsystem, we may assign infinity. Depend our problem need. Yeah, because I need to solve some problem. Yeah, I need to trying to assign 0 to indicate they are unconnected. Sometimes I need to use the infinity to assign infinity. So that I know that this particular edge is not connected, or I should not trying to use it. Yeah. So that is just the purpose. So even infinity in how they actually implement in the real world, normally they just assign a super large weight to that particular link between U and V. Yeah. Just a very large as you can. To some number is unreasonable large. So impossible that when you're trying to optimize your graph, trying to solve some problem, to search, for example, I'm trying to search the shorter path from one point to another point, from point A to point B. Then you put infinity or put a huge number, 100,000, 1 million weight. Of course, you definitely won't select that particular edge, because even sum out all the rest, you also won't be exist 1 million. You select one edge, you already increase your cost to 1 million. Yeah, that definitely your algorithm won't go and select that particular edge. So your problem still work. Your algorithm was still working, although you didn't assign the edge as infinity. Yeah, so that is the how in practice how we realize the algorithm. In theory, in the pseudo algorithm, in your pseudo code, in your algorithm, you can write infinity, but when you implement it, maybe not that easy. How to set this? Yeah, in the finite computer, you have to give a number. Yeah, so normally we just simply assign a very huge number to indicate that this particular edge is not connected. There's no edge there. Yeah. So for example, this is weighted. This is the weighted one. So not surprising, from here 1 to 25, I have 1 to 2. No, 1 to 2, there's a weight 25. So I put 25 here. Then 2 to 3 is 10. 2 to 4 is 14. 10 and 14. Then 3 to 5, only 3 can go to, 3 to 1, the weight is 5. Yeah. 4 to 2, 4 to 2 is 6. 4 to 2 is 6. 4 to 3 is 18. 4 to 3 is 18. Yeah, so this is the adjacency matrix for this particular graph. And this one is the corresponding adjacency list. Yeah, you can find that, yeah, now the number of list nodes here, they are only 6 nodes. Yeah, then just nice that I only have 6 directed edge. Yeah, for directed graph, it's not 2 times. Yeah, in fact, the directed graph, yeah, is based on the directed edge you have. So here I have 6 directed edge. So not surprising, the corresponding in the adjacency list, I have 6 nodes. Yeah. So it's 1 to 2, 2 to 3 and 4, 3 to 1, and then 4 to 2, 4 to 3. Yeah, and their corresponding weight will be stored in another field. You will have to declare, in short, your list node need to declare 2 variables. One variable store the edge, store the vertex, the adjacency vertex, and the corresponding weight for that particular edge. Yeah. So this is 2 way to represent the graph. Because once you can represent the thing into a matrix or into a linked list, yeah, a set of linked lists, yeah, then you can start use it to solve the problem. Yeah, because if you only have always the problem is like how you construct this graph. Yeah, you can do this way or this way, and then this way, you're not surprising that you need to use so many memory space to store. Your space complexity will take so much. This one, you take how much? Along here, you need V. In the list nodes, you need E. So many nodes. Yeah. Of course, you will say this one is one number. This one got 2 number. You got the linked list. Actually, it's got 3 number. Yeah, doesn't matter lah. You 2 or 3. In the end, it's still just a factor only. Yeah. So in what situation would we prefer one representation to another one? So you can see that the first one, if I choose one thing, you need to take notes. You will use more memory. You expect no matter how you compare this one and this one. But implementation wise, this one just a 2D array. This one is more complicated. You got 1 vector plus a bunch of the linked list. Okay, this is one issue you need to consider. Secondly, the time access. This one I want to know, yeah, if it's trying to know you give me the index. It's like the problem is like you give me 2 vertex. Yeah, I can immediately tell you that they are connected or not connected. I can immediately return you their weight. Immediately 25, no problem. Easier is like 2, you give me 2, 4, then I can tell you that their weight is 14. But this one, not really. you tell me 2 and 4. I need to check whether 2, 4 is the adjacency vertex of 2 or not. Then I need to check the linked list. 1 is a linear time reading. It will take the linear time to read. Yeah. But if you think the other way around, today you give me 1 vertex. I need to find all the adjacency. For example, you want to travel your graph. You want to travel from point A to point B to point C. Then when you are at point A, you want to know where is the next move. Where is your next vertex you can go? You need to find out all the adjacency vertex to A. Then this one actually not very good because you need to check every vertex whether they are connected or not connected. You need to find all the non-zero element in along here. But this one instantly tell you that number 2 is the adjacency vertex. So you will find that this one will be faster. So it's case by case. Sometimes matrix is better. Sometimes the adjacency list is better. There's no universal solution. In fact, this is too typical, classical representation. Of course, depend on the problem you need. Sometimes you will create other kind of a representation. Okay, in what situation? So weight the name of the vertex. The weight is this one is on the edge. In fact, all this one is 1 or 2 or 3 or whatever name. Actually, there's no. It's just a naming only. It's just a label. To graph, actually, not. It is for your implementation convenient. But to graph, actually, I just write in. This is a graph. The label is not so important. You want to label which one is 1, not the issue. So each list nodes will have a vertex and weight. Each list node for the weighted graph. For the weighted graph, yes. You need two elements. That means in the weighted graph, the linked list, the list nodes you need to have one is about the E. Maybe I use an integer to store. I need another one is the weight. Okay. Of course, actually not only. I think in practice you find that letter more complicated. Like we're talking about the flow, then maybe you can have another factor called capacity. Then I need to introduce another capacity. That's in each edge not only contain one weight. You can have 2 weight for different purpose. Then you can introduce another one. There's no any limitation. Your graph must be look like this or look like that. There's no particular structure you always have to use. So same thing. Actually all the data structure you learn so far. A lot of time we just like, for example, simple example, so we use integer. Doesn't mean that the item only can be integer. It can be anything. It even can, like this one, you can see that is an array. Then each element is a pointer. It's a linked list pointer. They store the linked list pointer. In this array, all are linked list pointer. Linked list pointer is the head pointer to one of the linked list. Okay. So I hope that you all know. At this stage, you should know that graph, there are undirected graph, directed graph, weighted graph, unweighted graph. Then you need to know what is the path, what is the cycle, what is the vertex, what is the edge. Basically graph is formed by a set of vertex and a set of edges. Then data structure wise, you can use to represent graph. Adjacency matrix and adjacency list is typical data structure we will use. But I would say that not only these two. Sometimes we even don't have to. Later you may see some example that it's a graph problem, but you not really need to construct the graph and then store it somewhere. We can solve the problem at the same time we construct the graph. That means we just trying to check where we have the raw data. Like later you will see. Actually we don't really physically really go and create a graph and then store it. Yeah, just like what you see just now, I show you the example, the one of the application. You can see that you give me a picture. I want to find where is the foreground and background. I don't really need to really go and create a graph for that particular image. The graph means that every pixel they represent a vertex, and then the adjacency pixel is there's an edge. I don't need to really build out this thing. When I want to solve the problem, I just go and check. All these pixels are represent the vertex. All these they are neighbor. So all of them are having an edge. But I don't go and construct. When I solve the problem, I just based on the algorithm directly go and access the raw data and then take the information I need to solve it accordingly. Because construct that graph is very time consuming and pointless. Later I also just run one algorithm to solve the problem I need to solve. I don't point to there's no in fact in practice I try not to do that, because that will increase my computational times. So that is the thing. Okay, so one of the typical problem in graph is graph traversal. Because you always got a very complicated graph, then one thing you want to do very likely is I want to visit every node to do something. Then the question is like, how do I ensure that I visit every node once? And do something once. So there are a lot of ways. Here we introduce two, the breadth search and depth search. So it can help us to solve some real world problem, like finding the shorter path or finding some solution. After visit every node. Maybe every node is the possible solution. But compared to tree graph, the challenge is like you visit this one, maybe you go here, you visit this one, maybe you go here, you visit this one. But the problem is like how you ensure that you not go back to the first nodes which you already visited. Maybe change another color, maybe clearer. First, maybe I visit this one. Okay, no problem. I visit, then I know that this guy is neighbor. Then I trying to visit this one. No problem. You trying to visit this one? No problem. Then when you're trying to visit this one, you know that this guy is his neighbor, and this guy is his neighbor. You need to know that this one is already visited. You should not go and visit it again. So maybe you will choose this one only. Then the question is like, how do you design an algorithm, very systematic way to visit every node? So that's why here got breadth search and depth search. Very similar. I suggest is like after this one you can go and compare with your tree traversal. They got some similarity. I would say that tree traversal is a special case. Is a special case of breadth search or depth search. You can see. Okay, so for example, breadth search is a level order traversal. It's a level order. What does it mean? It's a very systematically expose the edge directly connect to a vertex before visit the next vertex further. So example, I start from 11. So I'm trying to visit the next two vertex is 1 and 2. Then after that, the next level is 4, 3, 6, and 5. 4, 3, 6, and 5. Then next level should be, I will visit the next one. This one no more already. 5 have no more neighbor. Then 4 also don't have any next vertex. Yeah. So you want to visiting the vertex further away. After you visit 4, 3, 6, 5, I expect that you will go to visit 8, 7, 9, 9 and 10. Yes. Yeah, you can see that you are trying to visit the vertex further and further away from 11. Yeah, from the initial vertex, the first vertex. Yeah, the distance from 11 to 1 is 1 edge. Then after you visit 1 and 2, you start trying to visit the 1, 2 edge away from 11. So which is 3 and 4 and 6 and 5. After that, you're trying to visit the vertex is 3 edges away from 11, which is 8, 7, 10, and 9. Then the last one, this guy, 12. So indirectly here also tell you that from 11 to 12, that is the furthest path you can go. Yeah, 1, 2, 3, 4 edge. Yeah. Okay. So that is the level. You can see that there's a level order. So breadth first search is the level order. So from the first 1 edge away, 2 edge away, 3 edge away, 4 edge away. Yeah, from the initial. So that is first thing. Second thing you need to know. Yeah, so I need to provide you the initial vertex. You start from different vertex, the result will be very different. Not surprising. Can try erase all. Maybe I start from this one. Then the next visit nodes will be 8. The next visit nodes will be 3. Then the next visit nodes 1, 2, 3. So 1, 2, 3. 1. Yeah, the next visit nodes will be this one. This one. This one. And this one will be 1 and 7. Then the next one will be, this one will be visit 4, 11, 2. Yeah, 4, 11, 2. Then after that, you will visit 5 and 6. Then you will visit 9 and 10. Yeah. So you find that you start from different vertex. Your travel, not surprising that your order, your visit order will be very, very different. Yeah. But you can see one common thing is like they are level order. You always visit the nearest vertex first. So how to achieve this algorithm? You can find that actually I'm trying to queuing. So when you visit 8, okay, the next one is visits 3. When you visit 3, you need to start queuing 1 or 7. Either you visit 1, then 7 need to queue at the back. After you visit, expose the vertex 1. You know that sooner after that, a while you need to visit 4, 11, and 2. Yeah. So there's a queuing. You play this thing a few rounds, you notice that you actually are doing something queuing. You're queuing the order. Yeah, the next visiting nodes, vertex somewhere. Yeah. So to do so, not surprising, I need a queue. I need a queue to help me. Yeah. So for example, this is the directed. You also apply on the directed graph. Not on, just now the example is undirected. This one is undirected. Now we show you another example in directed graph. So let's say I start from A. So A is neighbor got B can visit. Later I also can visit C first. Then I also can visit F. Yeah, B, C, F, these three guys. Maybe I need to visit in, yeah, so to ensure your code always generate the same result as my one, so I probably have to define it clearly, saying that is the order B, C, F. There's no right or wrong. To visit B first or visit C first or visit F first, there's no right or wrong. It's just I want to have the same output. If I want to have the same output, I need to provide the order to you that must be in alphabetical order. Then of course I will visit B first in that case. So here I'm trying to visit B first. So after visit the B, I know that from when you visit the B, you will realize that there's another neighbor which is not exposed, which is D. So I will record now. So you need to have a queue to store that the B, just now is the B, then followed by C, followed by F. Yeah. That is after you visit the A, you know that it has three neighbor. A has three neighbor, which is B, C, F in alphabetical order. I will put B, C, F in the queue in this order. When I visit B, I find out that B got another neighbor, which is D. Yeah, which is D. Then I will add enqueue D into this queue. Then after that, I start trying to visit C. I visit C. When I visit C, okay, C, unfortunately, there's no neighbor. In the directed graph, there's no neighbor for C. So fine. Then I carry on to visit F. Then F, unvisit, more precisely, I should say unvisited vertex, unvisited neighbor. So for F, yes, he has a neighbor. He has a neighbor C and A, but both of them are already visited. So no new neighbor can add. So in this case, I carry on to visit D. Yeah, so D is visited. And then D, I can't find any unvisited neighbor. Then the algorithm will be end at this point. So, which also indirectly tell you that if you start your journey from A, in this directed graph, no matter how you do it, you won't be able to visit this guy and this guy because they are not really connected. They are not strongly connected. That means you cannot find any vertex from A to G. That you can't find any path, right? From A to G. You can find a path from G to A, but you cannot find a path from A to G. Agree? So breadth-first search, you can see I need a queue to help me to queuing the order, the vertex visit. What is the order? Visiting order. The visiting order. So it's a first in, first out matter. Because once you find out all the unvisited neighbor, you will put them in the queue. Then you will visit them in order. So the nearest one will visit first. The further exposed one, you will visit later. So you need a queue. So that is the breadth-first search. So summarize the algorithm. You expect that where's my cursor? So you need a queue. You need to first you enqueue you yourself, the first vertex. So you need to provide an initial vertex. Then you mark it as visited. So the very first vertex is visited, just like A. Then not surprising, you enqueue A. Always you first do that, then definitely at the beginning this one is not empty. Then you will just dequeue the A out. Then you will try to check A who is the A neighbors. Yeah, who is the A neighbors. Then you will, yeah, all of them, yeah, as long as they are unvisited vertex adjacent to the W, the A, for example, in this example, A, then you were trying to mark it, yeah, mark them as visited, and then trying to enqueue them into the queue, standby. Yeah, so you keep doing this, keep doing this, keep doing this. Eventually, yeah, all the connected vertex will be visited. Yeah, those like just now the example. Okay, yeah, you can see in the end, yeah, B, C, F, D will be visited in this order, but E and G you won't be able to queue them because you have no chance to find out any one of them. Yeah, they are not adjacent to any one of the vertex from A to B to C to F to D. Now none of them cannot be. So E and G eventually you have no way to visit it from A. Yeah. So that is the breadth-first search. Okay? Okay, just nice. Today I think I can cover the depth-first search. If a vertex has a several unmarked neighbor, yeah, like this one already explained. So it will be equal correct to visit. So I can visit, this one is like just like I mentioned, the B, C, F. You want to visit this one first, or this one first, or this one first. There's no right or wrong. Yeah. So, but quite sure is like as this level must be visit first. Yeah, you visit A, then the next one will be B, C, or F. Either one of them in any order. Also can C first, B letter, F. Then after that, the next level will be D. Yeah, just a E and G because they are not neighbor, so no way to visit them. Yeah. So through this approach, what is the application? One of them is finding the shorter path from S to V, from the starting point to any vertex. You can find out the shorter path. Yeah. So which is the path with the minimum number of edge. Then B, breadth-first search. Find the shorter path from S to all the vertex, reachable to S. Just how E and G is not reachable. Then you can build out the tree. Yeah. So the tree called breadth-first spanning tree. How does it look like? Do I have? No. Okay, back to this one. So the tree will be A, because A neighbor is B, then C, then the F. Then in this case, I will make D is yes. So in this way. So this is the breadth-first search tree. Breadth-first search tree. Breadth-first search spanning tree. Okay, of this example. So because just now I mentioned that the order, yeah, they can be in any order. So will it be this spanning tree is unique? What do you think? The breadth-first spanning tree, is it unique? For any graph, will you get? I mean, give you the graph, give you the initial vertex. I give you the same initial vertex. Will you be able? Is it the spanning tree is unique? Yeah, I give you the same initial vertex. The first vertex is given. The S is given. The S is given. Yeah, I give you the same S. Yeah, same graph. Directed, undirected. Yeah. Breadth-first spanning tree. Is it unique? you start from A. This one is B. I think someone said no lah. I hope you understand my question. So yeah, I think it's no lah. Because you look at this one, if you start from A, yeah, you select B first or C first, will decide the neighbor. Yeah. So yeah, you can have. Yeah, you can have. So the spanning tree start from A. I build B and C. Yeah. Then depend you visit B first or you visit C first. Then you will decide the in the queue D is belong to B or C. Yeah, it can be here, nothing wrong. Yeah, the next node can be here. The D can be here. The D also can be here. Yeah, this both spanning tree represent the breadth-first spanning tree to this particular graph. Yeah, so both are correct. So in other words, yeah, it may not be, it cannot be unique lah, I think. Okay, so that's breadth-first search. So basically, the application, yeah, it can be finding whether, yeah, they are strongly connected graph, directed graph or not. Or you also can check finding all the vertex within one connected component. Yeah, you also can find the shorter path between two vertex, and so on and so forth. Yeah, there are a lot of application for breadth-first search. So sometimes maybe not so obvious. I think, yeah, I tell you this is breadth-first search, then you apply it, and or you see the problem, you know that you can use a breadth-first search to solve the problem. I think it's different way to think the problem. Yeah, the tough problem is like you see this problem, you don't know whether you can use breadth-first search or not. Yeah, especially when you learn more and more. I think that's why you learn one or two algorithm, you find that actually quite easy to do. But actually in real world, when you learn 10 algorithm, there are 20 algorithm. Yeah, there got hundreds of algorithm. Then how do you know that this problem can be solved by breadth-first search or depth-first search? Or in the future, you will learn ditract algorithm, prime algorithm, or a lot of this kind traversal algorithm. Yeah, I think that is the difficult part. Yeah. But one thing is this thing is the level by level traversal. Yeah, level order. So then the time complexity for the breadth-first search is each edge is processed once, while loop, and then so each edge, because you visit this one, so you visit each edge. Yeah, so all these edge and most ones only. Yeah. So you will check all its neighbor, like just now the example. Yeah, maybe something like that. Okay, anyhow draw. So you start from A, you visit this edge, you visit this edge. So you know that B is here. You know that C is here. You visit this one, visit this one, visit this one. Yeah, you know that this one is unvisited nodes. This one is unvisited nodes. This one is already visited. So later you will visit D and E. Then after you check this, then you find that everything is visited. So the while loop total cost is only E. Then the vertex at most E at most is V. Then you queue and dequeue. You queue in, you queue all the vertex once. You dequeue only all the vertex once. So at most you only visit 2V only. So, but it depends on your implementation. If you use an adjacency list to visit, you may modify. Yeah, if you want to modify, possible lah. If you modify the breadth-first search, can it be? I want to find the E and G based on just now the example E and G. Can I visit the E and G? That means you need to know all the vertex. So after you travel to a level, you find that you already no more neighbor. You have to reinitialize a new unvisited vertex and then carry on your journey. I think, yeah, you can say that is a modified version. but quite easy to modify it. Yeah. So so in the worst case, your breadth-first search traversal, you can see that adjacency list is only the V plus E, because I have the one array, then each of them have a linked list. Yeah. So when you visit this guy, you queue this one and queue this one. Then later you dequeue this one. You trying to visit this one. Then you just enqueue all this vertex. Yeah. So in the end, your complexity is V plus E. But in the matrix, it's different story, because matrix you have a V by V matrix. Yeah. Whether they are connected or not connected, you have to check, you have to check, you have to check, you have to check. You have to check all of them one by one. You have to check them one by one. Yeah, when you visit or not visit, you need to check whether they are connected or not connected. So not surprising that the time taken is like V square, because you take V to scanning one whole row. Yeah, it takes times. So this one look better. Yeah, this one look not so good. Okay, so that is the breadth-first search. I think today already run out of times. Maybe Monday I'll cover the depth-first search. Okay, so we still have already slow down the things. So depth-first search will cover. Then maybe I think probably Friday I can delay the assignment 7, 8. 7 and 8 I will combine into one assignment. I'm trying to release it as soon as possible in this today or Friday. If today cannot, probably tomorrow I also don't have time. So I will release it. If today I can't do it, then I will do it on Friday. Then the deadline will be all the way to week 13. Then this thing will cover on Monday, depth-first search. Yeah, then on Monday morning, 10:30 to 11:30. Then Wednesday will cover the Queen problem. Yep. Okay. So is there any? Okay, I will answer this. Good. Okay, today no question. If not, I will end today's lecture. Okay? Thank you.